Well, welcome. This is talk about computer-based math, which I'm sure we have now been going for 6 years, since 2010, when Conrad Wolfram founded it. So I'm here to kind of give you the latest into what computer-based math is up to. We've had quite an exciting year. We've made some significant changes to what we're doing, and I'm here to kind of introduce some of those things to you today. But for those of you who aren't familiar with computer-based math, CBM was founded to push a real reset on the school subject of maths. Forgive me if I say maths. I am British. I've put math in here just in case you want translation. Basically so that it reflects the real world subject. I mean, a lot of us here anyway are math lovers. We've used math in all different guises, most of us to, some of us to a very high level. And the educational subject of maths is not the one that we know and love. So CBM was founded to try and instill this kind of thinking right from the very, very early stages. And this really can only happen if we engender computational thinking. Computational thinking being a process by which we can attack problems, by which we can actually use the computer as a tool to kind of help us reach the solutions that we want. So the last two lines is a statement that is fairly obvious. Use computers in school as we do in the real world. We don't want to use gimmicks. We don't want to use kind of base level educational software. We want to use real stuff that real people use, and we want to get a whole generation of people to use it. And that is to replace humans for calculating. We've known for ages that a computer can calculate, can compute much more than any human can, and it's about time that education kind of really hears that. So, why are we doing this? This is a quote from Conrad. Computers have liberated real-world maths from hand calculating to go further and faster than anyone could have imagined. Now it's vital that educational maths stands on this automation too. Basically, we have all of this at our disposal. We have, we have a wonderful system in Mathematica, and Wolfram language, which we choose to use for our materials. But computation in general has kind of liberated real-world maths, and we need to do that in education. So, how is CBM doing this? So, we're building a new high-concept maths curriculum, basically assuming that computers exist. So we have computer-based computation at its heart, and we're redefining maths as the anchor subject for computational thinking. We're doing many discussions at the moment about how computational thinking relates to CBM, but basically it relies on a skill set which is partly about how to structure things, how to kind of numerical quantitative reasoning as well. And math seems to be the anchor subject in CBM form for computational thinking. Now this has applications across many fields. This is what we've found when we've been building our materials, is that this has tentacles in all subjects. It has tentacles in geography, it has tentacles in history. It really kind of covers a whole multitude of things, but we can kind of center that on problem solving, and CBM is contextualized within a maths concept area. So this is a nice manipulate, which is basically a representation of what educational maths is right now. We believe that the 4 steps of our problem-solving cycle are the definition of your question, the translation to maths or some algorithm or code, and an abstraction step. Then you have the computation step, which is where you get your answers. It's where it's where you scribble furiously on your pen and paper, or you use a machine to do it for you. And then the 4th one is an important one as well, which is your kind of critiquing step. It's an interpretation, it's a recontextualization of what your original problem was. Now, what education is doing right at the moment is that they're paying very little attention to those 3 areas, which are smaller, and spending a huge amount of time teaching hand calculating techniques and learning things by rote, and without kind of a thought to the underlying principles, or kind of or the outcomes that they're trying to achieve. So the CBM solution really is to kind of get a more balanced view of things. We want to kind of augment the other 3 steps, and we want to be able to use computation and use real-world tools so that all of these other 3 come back into focus. Now, these are real skills that that students need, and we think that the curriculum should embody all 4 of these things. The way we're applying this is in what we call the CBM solution Helix. So this is not a kind of a one-time thing. This is an iterative process that you can go through this solution many, many times. You're refining, you're experimenting, you're defining multiple questions. And so you have this kind of helical approach where you're going through your various different stages of the cycle, ultimately refining and until you reach some solution at the top and achieve infinity. But this is basically the process on which CBM is founded. And we've done a lot of thinking about this in the past year and how that relates to kind of what we're building. So what's your problem? I mean, the way that we develop our curriculum materials is that they are problem-centric. We don't ever approach things from the perspective of, we've got to teach some standard deviation right now. Let's think of a contrived thing that we can put so that we can teach standard deviation. It's like, well, what is a problem that we want to solve? We have, and I'm not going to show you because it would be embarrassing, we have a massive spreadsheet of all kind of brainstormed questions that we could make modules from. And some of them are like, would I survive a zombie apocalypse? Through to, how many friends do I need to friend on Facebook in order to like meet the Queen or something like that. They're kind of problems that people really want to solve, but the ones that we've been concentrating on in our statistics curriculum and things like that are, am I normal? We have a kind of have a set of different things that we're using. We have ones in geometry, like how can I create a flat map of the world, and that kind of goes through all kinds of different mapping tools and ways of abstraction there. This is really crucial, and this actually is, for us, quite a difficult part of the process because we have to map out a curriculum that covers concepts and tools that we want to expose people to, but in the context of real-world problem solving. And what's the outcome of this? We've done some extensive work. This is actually new. These are our required outcomes from mainstream maths. This is on the ComputerBased Math website. If you have the talk, I've put the hyperlink in there. But we've split these up into 11 different outcome areas, and they're all split up into kind of outcomes that we would like the student to be able to be capable of. So we actually tag these in all of our materials so that teachers can see these through. And the critical thing here is that some of these dimensions are directly aligned with the solution helix. So defining the question, these are all of the outcomes that are related to that first initial stage. We have the abstraction here, which is heavily in stage 2. And then when you get to tools of maths and managing computations here, you're kind of in the computation, in the compute your answers phase of the helix. And this is really important. A lot of people who are designing outcomes, especially problem-solving outcomes, try and squash everything into a process. Now, what we're saying is there are some dimensions here, communicating and collaborating, that sit outside of the process. These are general outcomes that you need as not just as a mathematician or a computer scientist, but these are skills that you need in order to be able to collaborate your work. And then this is something that will help cross-curricular as well. So there are some that sit outside of the Helix and some that very definitely set into it. If you want to download the PDF, you can. We've done quite a lot of work on this, and we've hoped that the explanations really kind of say what they are. So, given that we've been working on a lot of things, I thought it would be appropriate to show you one of our latest modules. We have been working with the National Irish Assessment Board to do a module in modelling, and this is part of their kind of problem-solving curriculum. And as part of this, cycling is big in Ireland right now. It's kind of a bit of a buzz thing, and we've developed this module, which is how fast could I cycle stage 7 of the Ampost Race, a really famous cycling race. For those of you that haven't seen our materials before, they're split up into a hierarchy of chapters, of activities, of modalities below activities, and then review sections. We try to use questions as the framework for the materials. So the module question, how fast could I cycle this stage? But we've broken it down into different questions. What are models and what can they tell us about cycling? It's an investigation into modelling as a whole. And then specifically, how do I break down my question? How much energy is wasted from rolling along? How much does air resistance slow me down? What effect will the road's gradient have? And then finally, consolidating my model here. So we kind of do a combination of exposure to things. This is our teacher view. You'll see our kind of technical manual here. These are all features that we've put in so that the teacher could do this. In the student version, which pops out here, all of these things are suppressed. We expose them to a model. We basically don't give them anything. We say, go play with it. How is my power being affected by my rolling resistance? What effect does the gradient have? Getting them to think about concepts. Getting them to think about concepts before they actually try and break things down. And then we ask them questions about formulating their question. The vast majority of the first chapter is about defining their question. Once they've defined some questions, we kind of get on into the breaking down the problem. And this is a guided learning approach. There are 3 facets to CBM. This is very guided. And then we also have kind of a less structured approach, which is our projects at the end, which scaffolds some of the stuff but doesn't walk them through it. And then a project-based activity is kind of the least guided. So we encourage them to kind of use our image processing tools here. So they're taking actual frontal area pictures of themselves so they can find out their own frontal area and how affects that their air resistance. And the good thing about this also is that we bring the problem-solving cycle to the fore. All of our modalities are tagged with a part of the solution helix, if appropriate. And so they can see really where they are in that system. In review, we have a chapter review, and we make this very clear that it's segmented into the different parts of the helix. So we're asking them questions about definition. What assumptions have you made? In the translation here, it's kind of more about how did you abstract this? Explain what you've done with your frontal area. What formulas are you using? And then the computation here is kind of what value did your model predict? We're checking that they've really kind of associated these things. And then we also prompt them with critiquing and interpretation questions as well. This is a new part of the materials. From feedback that we had from several of our pilots, it wasn't inherently obvious that we're actually teaching the problem-solving cycle first and foremost, and kind of maths concepts and contextualization second. It wasn't kind of, we wanted to kind of represent that visually. And that's been really clear, and it also helps as a guide so that when people are thinking about approaching problems of their own, they have kind of like a 4-step markup to do that. So I thought I'd show you a bit of this in action. As they're going through their notebook, they're kind of defining all of their forces. So their force 1 is their rolling resistance, their force 2 is their air resistance, and the force 3 takes into account gradient. And they're building up these power models with the things that they've kind of included in it. Obviously, I haven't spent an hour doing that, so I have my model definition here. But I figured that most of you probably wouldn't care how fast that we cycle to around Ireland, so I thought we could cycle from Champaign to Chicago. So we've built this tool here. We're very much about kind of giving people real things to use. And we have the route here. There's just a normal GPX route. We're using real data. And what this tool done is it segmented it into different sections here based on gradient. In fact, you're very, very lucky in that I don't think there's like any proper hills here. So you should be able to do that. You should be able to do that really, really quickly. If I said on Google Maps it was going to take me like between 12 and 13 hours, and I figured it'd probably be quicker to fly. But this is it, and then this is where they can kind of see what's happening. This is the model that they've done. I'm going to paste my formula in here. What have I called my velocity argument? Oh, I'm being very, very, and what power are you using? And then I'm going to run my model, and the model is then computing, given all of the things that they've put in, their velocity and their time for the different sections of this. Now, they can apply this to anything they want. We've asked them to apply it to the stage 7 of the Amposter-Ras, but they can apply it to anything they like. But the really important thing here is that they can see immediately the effect that the model that they've chosen is having. So this says at a power output, a continued power output, which as a cyclist makes me go weak at the knees, of 120 watts, they would have. It'd take them 10 hours and 35 minutes, which is about 2 hours quicker than Google says it is. But if you kind of change this, and we can say that I'm going to be really slow today, then actually it's going to take me 13 hours, which is probably much more appropriate. So this is something that they can then play with, and we ask them in the following sections to really critique this. Could you really cycle the stage in that time? The answer is no. They're looking at data from actual cyclists doing this, and we've exposed them in the previous parts of the module to. We have some videos from some famous Irish cyclists as well, and some real cycling models. And if you've ever seen a cycling model, it's got 5 billion different variables that they can use. We've only taken 3 effects into account. Okay, they are the major effects, but we want to kind of get them to think about, well, what's the next stage? What could they do with that? And at the end of the module, we've got here the project, which is about applying what you've learned in this module, but in a guided way to a completely different problem. So we've got this problem of finding your maximum minimum velocity during a free-fall skydive. And instead of taking them through this, what we've done is we've segmented it into the 4 different Helix areas, and we're giving them probing questions. I'm not sure if you can see this, but what information do I need? What factors change during a free fall and which are constant? It's probing them with questions. What physical relationships or equations apply to this problem? And it's kind of scaffolding them. And then of course we give the teachers some hints as well. These orange sections won't get seen by the students. So this is all part of it, and this is the part where the teacher can really engage in what they're doing, and it's a much more kind of creative approach. So that's basically what we've been doing with our module right now. So where are we going? We have some really exciting pilots and projects on at the moment. We're in a second pilot phase of our statistics curriculum, which is rolling out in schools in Estonia. The Estonian government had our statistics curriculum. We're rolling out the second pilot. We have a project in Africa at the moment. We have links with Sweden, and we also have this collaboration with the Irish Assessment Board as well. One of the key facets of CBM and any kind of curriculum in general is how do we assess this? And we've been talking to some major assessment bodies, including national assessment boards in the UK and in Europe, about kind of what is the best way to assess CBM. And it's a different way from traditional maths. It's about having a kind of more kind of creative marking process, maybe project-based assessment, allowing people to kind of assessing their thinking rather than just the actual output. And then cloud-based CBM. We're obviously a huge facet of what we're doing. All of our projects right now have site licenses of Mathematica. All of our Estonian materials were deployed on CDF Player. But now we've got some robust cloud technology for deployment and for access. We are migrating our materials over into the Wolfram cloud. Obviously, everything that you've seen today is written in Wolfram language. That's the framework that's completely built out of Wolfram language. You don't use anything else. And so we're kind of migrating things to the Wolfram cloud and hoping to build some kind of deployment mechanism around that. So as a pet project, I wanted to show you our new website. For any of you who haven't visited the ComputerBased Math website, you won't see a change, but anyone who has seen the ComputerBased Math website, you'll see a significant change. And I just wanted to leave you with the little animation that's on the top of the page, which is trying to tell the story of kind of how computer-based maths can fix the current education crisis. And this was even before 3D printing came in. Okay, if you have any questions, just let me know. But thank you very much.